because then I don't have to put it in a slideshow mode. It kind of freaks out when I do that. Okay, so if you want to write into your brown bombers, think of it as a formula. That's my tip so that you can use it. So you have a transformation of two variables. This is a two-dimensional thing. So you have a joint PDF, and not an easy joint PDF that you might have that it's independent. The one I'm going to show you is independent. That's why I call it a toy problem. But this works for anything. So if they give you a joint PDF that doesn't have independent pieces, then you can use this. So the trick, the hard part is that you should be able to solve for this y1 and y2 in terms of the u1 and u2. So I'll show you where that piece is, because you kind of have to have a trigger place to know when to stop, when it's not going to work. And it's not going to work if you stick this on Mathematica and you can't solve for y1 and y2. That's when it's not going to work. Then the transform PDF is equal to the original PDF with this inverse function plugged in for the y1 and y2 times the absolute value of the determinant of the Jacobian. So to me, when I look at something like that, I'm thinking, that's an algorithm. I just plugged through the whole thing. So today, Colonel Clark came to my office, got one of my analysis books, because he's looking at, why this happened. So he's going over that with his students, and I'm feeling a little guilty that I'm not doing that with you, because it's actually a very cool thing. It's multiple dimensional changes in variables. So you're changing, in one dimension, you're changing your interval that you're integrating over. You're actually moving around integrals around, the interval of integration, so that the integral looks easier. In multiple dimensions, you're integrating over an area, and you're changing that area so that your integral becomes nice. And the Jacobian is the du part in that change of integration. So that's what it is intuitively in the double E kind of method of explaining things. But he's actually going through, he was asking me about isometries today. I'm like, okay, I don't think we're going to do isometries. But hopefully he doesn't think that's a good thing to ask on the WPR. That would be hard. So I'm going to give you a twin example from the book, Stepped Out. So in these kind of problems, just like any kind of problems, you're given two independent functions, but really what you'll be given is this guy over here. And it doesn't necessarily have to be separable. So you don't have to be able to split it or anything. That's what's good about this method. So this f will be given to you. In this particular toy example in the book, they gave you independent random variables so that you don't have to worry about it's split up already. So of course the computations are all easy. But this would be where you start. Somebody's going to hand you this, and they're going to hand you this, the transformation, and they're going to ask you for the PDF of the transformed variables. So I copied and pasted the picture, so if you didn't get it all, that's what's given to you. The first step is to solve for y1 and y2. So you have two equations and two unknowns here. So if you remember from MA 103, you just put the system in. I forgot what the command is for, is it capital solve? And then you put the system in and it tells it to solve, and it solves for you. This is where this process will break down if you're not able to solve and get the y1 and y2 in terms of the u1 and u2. So here it was easy, just stick it. Yeah, you can do this by substitution method by hand. So this one was fairly easy. And that's your H inverse. So the H inverse should be something that you can actually find in closed form. That's what messes up the T equals Q squared problem, actually. That's exactly what that is.
And do you need two transformations in order to use this method? Like how you're given U1 and U2? Because there's some instances where it's still bivariate, but we only do one.
The U is equal to Y1. In that case, what they really want is a marginal. If you've looked in the book and looked at what they're doing, they're looking for a marginal one, right? So here they're asking you for a multidimensional version of what we did earlier. Right? This is the transformation method in multiple dimensions. That's what this is. The Jacobian is actually the first derivative in R2. That's how you can think of it. It's analogous to the first derivative in R2. That's what it is. So a second step is to find the Jacobian. Your book calls the determinant the Jacobian in one spot, and that actually later on calls this matrix. Please close your laptops. It actually calls this matrix the Jacobian too. The matrix is the Jacobian. So what it is, it's the partial of the first function with respect to the first variable, partial of the first function with respect to the second variable. So first row is just first function, second row is second function. It's the partial derivatives. And it turns out, because this is a toy problem that they made up just to introduce you, everything's easy. They're all halves or minus 1/2. So it turns out you get half, half, 1/2 minus 1/2. The Jacobian is a very, very cool thing. So there's a multiple dimensional Taylor series. There's a multiple dimensional. That's the whole reason we do work with R2, R3. That's what we do. Linear algebra, all those things make us work with multiple dimensions. We're actually doing something with a group in Germany that is used to working with one dimension. And they keep talking about adjusting for a variable. We're doing PCA. And so, you know, the junior faculty member that's with me keeps explaining that we cannot see in 6 dimensions, but we are reducing everything to 3 dimensions so we can see things. This idea of working with these kind of structures is what allows us to do those things. And so, you know, he walked out later and said, it's best if they take linear algebra. I don't think that's happening. Since they're doctors and they're probably not going to sit in a linear algebra class anytime soon. Those days are gone. Next step is to find the determinant of that thing. Don't get on Mathematica to find a determinant of a 2x2. All right, so that's minus 1/2. And then you'll need actually the absolute value of this guy. So they have that. What annoyed me is they had the symbol for absolute value around the Jacobian, but that's also another notation for determinant. And they're calling something determinant. So they were so precise up to this point, and they're kind of like going nuts here. But you want the absolute value of this determinant in your final answer. Then you're going to plug in those transform variables into your f of y1, y2. So that's all you do is a substitution. So you just plug in your transformed, your inverses in for the y1 and y2. Just to have you recall, this is where we started out. So you're just plugging and chugging inside those two things. And it is a plug and chug. You just crank it through the formula. So this is your plugged in stuff here, and you multiply by the absolute value of the determinant of the Jacobian. And that's your joint probability distribution function in terms of the U1 and U2. So remember I told you this is an easy thing to do, and you can use it. I would go through those other examples. If I have time, I'll try to make videos of them so that you can see them stepped out. But this process is the same, and it's pretty easy to do. And I think you can probably use it on some of the homework problems that you're using today. It still won't change the fact that Colonel Watts has moved the support to the box 1, 2, 1, 2. That problem still exists. You still have some issues with that. So it's not a fix for everything. But it does help on some of the problems. So maybe one of the problems you were thinking of using moment generating function and it's getting messy, you can use this. Okay, any questions?